So we talked about Dalton's atomic theory, and one of the things he said was that all atoms of a given element are identical and have the same mass. We know now that that's not quite true, that there are isotopes, and because the isotopes differ in the number of neutrons, they're going to have slightly different masses. The mass of an atom is sometimes called the atomic weight. That's the older term. Now we prefer atomic mass. Atomic mass is the mass of an atom. We calculate an average for each element. So there are several isotopes for many of the different elements, and we give the average. Because in any sample of, say, carbon, you're going to have a distribution, a variety of the different isotopes. This average atomic mass is listed below the element symbol. Above is the atomic number, tells us the number of protons. Below is the atomic mass, and so this is the mass, the average mass of an atom in atomic mass units. So just like if you had some bowling balls, you know, maybe you had a 10-pound bowling ball and an 8-pound bowling ball, the average mass would be 9 pounds, right? Do either of the bowling balls weigh 9 pounds? No, they don't. But that's the average. So even though this is the average mass of chlorine, there's no one atom of chlorine that weighs that. But we almost never deal with single atoms of chlorine, and so what is useful to us is the average mass. These averages are calculated according to the natural abundance of each isotope. The percent of chlorine-37 and the percent of chlorine-35 are fairly constant no matter where you get your sample of chlorine. And so we calculate based on that average. So here's chlorine-35. Chlorine-35 atoms weigh 34.97 atomic mass units. Notice that this mass is very similar to the mass number. It's very close. It's not exactly the same, but it's really close. And chlorine-37 has a mass of 36.97 atomic mass units. 75.77% of all the chlorine atoms are the chlorine-35, and the rest are chlorine-37. So normally when we do an average, we add all the different things together and divide by the total number. Well, if you were averaging atoms, it would take you billions of years, and that's not very practical. So we use the percentages and do a weighted average instead of having to add up a gazillion numbers, literally a gazillion numbers. So these percent abundances have been determined experimentally, and those would be given to you. You don't memorize those. They're not hiding on the periodic table anywhere. What we do to calculate the average mass is we take the percent abundance and we convert it to a decimal form. We just divide by 100. So 75.77% becomes 0.7577. You multiply by the mass of that atom. So here's 0.7577 times the mass of that isotope. That gives us a value. And the other percentage converted to a decimal times the mass of the other isotope gives us a number, and then we add those together and we get the average atomic mass for chlorine. Any questions? This is also how your grades are calculated based on the different categories of grades. Okay, homework is 10%. So it's 0.1 times your average homework score, plus 0.15% times your final exam score, etc. But Canvas does all of that for you, so you don't need to worry about it. So in math language, this is how this might be indicated. The atomic mass is the sum over n of the fraction of isotope n times the mass of isotope n. So you do this fraction times the mass for each of the individual isotopes, and you add them together. Let's do an example. Magnesium has 3 naturally occurring isotopes with masses of 23.99 AMUs, 24.99 AMUs, and 25.98 AMUs. Natural abundances of 78.99%, 10%, and 11.01% respectively. Calculate the atomic mass of magnesium. This is not a dimensional analysis problem. We have to use a formula or an equation. We're going to take the percent abundances, convert to decimal form, multiply the mass by the masses, and add them all up. So the first one is 78.99. Converting to decimal, that's 0.7899 times the mass of that isotope. That's the first one, 23.99 atomic mass units. The second percent abundance is 10%, so that becomes 0.1000. We got to keep those significant figures. And we get 24.99, because that's the second mass. And the last percentage is 11, so that becomes 0.1101 times the mass of the last isotope. Okay, so now we get our calculators out. 0.7899 times 23.99 plus 0.1 times 24.99 plus 0.1101 times 25.98. Calculator says 24.309099. The unit would be atomic mass units. Any questions? What about sig figs? I'm never going to try to trick you with sig figs on here. Really what significant figures are for is so that we express a reasonable number of digits. So instead of trying to be super exact with sig figs, we're going to try to be reasonable. So I would consider how many digits are in my percentages. So here I've got 4 significant figures in each of my percentages. That's pretty good. And then I look at my masses, and I've got 4 in each of those, but more importantly, I have 2 decimal places. So what I'd like you to do when you do problems like this is look at your individual masses, and that's probably going to be how you express your average mass. So I would probably want to keep 4 significant figures, the 2 decimal places that I had in my other masses. The exception would be, what if this was just 79%? What if it only had 2 sig figs? Well, then my percentages are limiting the uncertainty in my result, the number of sig figs, and so I'd have to adjust that. But here I've got 4 sig figs in my percentages, and I'm proposing 4 sig figs in my average, so I think that's a good place to go. 24.31 atomic mass units. This is an actual element, and so we can check our answer on the periodic table. On the periodic table, it says 24.3051. So this agrees with the periodic table. That's a good sign. What we like to do on exams is make up elements so that you can't just find the answer on the periodic table. You have to actually do the problem. Any questions? You might wonder, well, how do they figure out the percent abundances, and how do they actually measure the masses of these things? We do this using a technique called mass spectrometry. It separates particles according to their mass. So looking at chlorine, we would see that if we say that chlorine 35 is 100% intensity from the signal of this instrument, then chlorine 37 will show up as less than that, and from this ratio we can figure out the relative abundances of the 2 different isotopes. So here's how a mass spectrometer works. You inject your sample, and it goes through a heater that vaporizes the sample. Now, even metals like iron, which is a solid at room temperature, at a high enough temperature you can vaporize these things, put them in the gas state. So you can vaporize anything. So we vaporize it, put it in the gas state, run it through here where an ion beam, an electron beam, ionizes the samples. Even things like the noble gases that don't form ions normally, if you zap them with an electron beam, you can force them to become ions. They're not going to be stable that way. They're going to react and do something else, but you can get them through the instrument being ions. We need them to be ions so that we can accelerate them. With a charge on them, we can accelerate them using electrical fields. So we cause them to go zooming through here, then they go through a magnetic field. The magnetic field causes their trajectory to bend. How much it bends depends on how much the particle weighs. If it's more massive, it won't bend as much. If it's less massive, if it's lighter, it'll bend more. And so where these things hit on the detector tells us what their masses are. The intensity of the signal is what gives us the percent natural abundance of the different isotopes. Any questions? We actually have a mass spec just on the other side of that wall. It's a pretty cool instrument.